Hello. All right. Let me get a couple things set and we'll get started. All right. Well, happy Monday, everybody. So as we get started, today we are going to start chapter 19. I will tell you that I am going to go ahead and do a PowerPoint. Actually, there'll be two separate PowerPoint presentations that I will record for chapter 19. One will be on balancing oxidation reduction reactions, which I'm going to cover today, but I'm not going to list out all the steps and everything. That will be in the PowerPoint, which I'll give you both a PowerPoint and a Zoom video of that. The PowerPoint I'll post right after class. The Zoom video of it, I will post however long it takes it for it to process, but sometime later today. I will also do a second PowerPoint over chapter 19, which will cover the remainder of the material. So I'm splitting it into two parts. And in order to cover oxidation reduction reactions, we need to remind ourselves of a couple things. First of all, what is oxidation? What is reduction? Okay, and the one that I like to use is losing electrons is oxidation. Okay, gaining the electrons is reduction. Okay, now we covered this in Gen Chem 1. You're expected to have at least seen oxidation and reduction. And remember, L-E-O, Leo says G-E-R, GER, all right? So Leo says GER. That's one of the ways we can remember it. I know some people teach oxidation is loss, reduction is gain, oil rig. I don't like that because it doesn't use the word electrons in there, so you don't focus on that. But if that's how you remember it, that's fine. Now, another reason that we call this reduction is if I'm gaining electrons, and the electron has what kind of a charge? A negative charge to it, okay? So if I add that to anything, so let's say I add that to an iron 3. If I add an electron to an iron 3, the iron 3 gains an electron, right? Okay, GER. What happens to its oxidation number? It goes down, okay? Now, if it's negative, it's going to go more negative. That's why it's called reduction, is because the oxidation number goes down. We don't need to worry about that too much, but we do need to pay attention to electrons being gained and electrons being lost. Okay. Now, a lot of you are fairly good at balancing equations, but there are some equations that are a little bit tougher to balance than others. Now, I'm going to start with a relatively simple one. Okay. And we're just going to look at the reaction of solid aluminum plus permanganate. And that gives us that's a 2 if I can write. Okay, so if you try to balance this equation, you're going to have a little bit of trouble with it. Okay, why? Let's see, I have oxygens here and I don't have oxygens over here. So I need one little bit of information in here that this is in an acidic solution. I knew my whiteboard wasn't going to be long enough for today's lecture, so I had to add another little one to it. So we'll go to that. Now, what does that mean that it's in acidic solution? Well, that means it's in, first of all of these are aqueous, except for, of course, the aluminum solid. And the second thing is acidic means it has a greater amount of hydronium than hydroxide. So that's going to be important for us in a little bit. And in order to balance this equation, the first thing we need to do is assign oxidation numbers to everything. Now, if you remember your oxidation numbers, great. But if not, you might need to go back in the book, back to page 127, where it goes through the oxidation number rules. And I just so happen to have put my book open at 127. And I'm going to read through those rules from there. And then I'm going to kind of summarize them a little bit, and then we'll apply them to this problem. Now, the first one is if we have a pure element, it has an oxidation number of 0. For example, aluminum solid is a pure element. Okay, oxygen. If I have oxygen gas, O2, its oxidation number is going to be 0. If I have ozone, O3, O3 is also going to have an oxidation number of 0. Okay. Second thing, in addition to having the element with an oxidation number of 0, any form of that element that's just a pure element is going to have 0 as an oxidation number. For example, ozone and oxygen. Now, second rule for monatomic ions, a monatomic ion, mono, one, atomic atom, one atom ions, the oxidation number is the same as the charge on it. Now, I have been fairly consistent about trying to have you write a charge with the number first. If we write the charge first, if I write a +3, +3 is an oxidation number. Now, oxidation numbers are not the same as charges. It's kind of a way of keeping track of electrons. But if I have a covalent bond, even though it's a polar covalent bond, those electrons are actually shared. But what we're doing is we're attributing all those shared electrons to only one of the two atoms and calling it an oxidation number. For example, in water, I know the oxidation number of water overall, H2O, is a 0, okay? Because this has just the exact number of electrons as it does protons, okay? However, if we look at this, we say, okay, the oxygen is more electronegative. I'm going to attribute those shared electrons to oxygen. So oxygen we're going to call a -2, and each hydrogen is going to be a +1. Okay? And I don't know who's not muted over there, but you might mute yourself so you're not hearing, everybody's not hearing you. Okay. Notice that the sum of the oxidation numbers is 0, even though I have a +1 here and a -2 here. That's because I have to take into account that I have 2 hydrogens that are +1 and 1 oxygen that's a -2. Okay, so that's the first thing that we've got there. Okay. Elements, monatomic ions, and if we look at oxygen, oxygen is almost always a zero. Oxygen is always a -2, unless it's an element by itself, in which it's a 0, O2. We see that quite a bit. Actually, we don't see it even though it's right here in front of us. And if it's in a compound like water, it's a -1. There's a couple exceptions to that. There's a couple ions that we have. One is O2 minus, which is superoxide. And I also have O2 minus, which is peroxide. You're probably familiar with hydrogen peroxide, H2O2. Okay, so the fun thing to do is, all right, what is H2O? H2O is water, right? What is H2O2? H2O2 is hydrogen peroxide. So what is H2O4? Well, it's for washing, it's for drinking and everything. So okay, so I had to tell that joke, all right? Fun little joke there. But as I tell that joke, I want you to remember, if I see something like H2O2, I need to remember, oh, wow, there's something almost funny about it, okay? So it's not the same as water. In this case, O2 2 minus, each oxygen is a -1. Now, superoxide, which we're actually not going to deal with, but it's kind of an important ion. Actually, if it's around in cells, it causes lots of problems. So there's this enzyme called superoxide dismutase that goes around and finds all the superoxide and converts it into oxygen. But in each of these, it's a -1/2. Now, we're not going to deal with any that have an oxidation number that is not a whole number for the most part, although I want you to be aware that they exist. But peroxide, we may see peroxide in some of the problems that we look at, okay? So that's the third rule. So normally, if you see oxygen, look to see if it's an element by itself. If so, oxidation number of 0. If it's combined with something, assume the oxidation number is 2, unless you recognize the hydrogen peroxide, or there's also sodium peroxide, potassium peroxide, things like that. Okay. So oxygen is almost always a -2. Now, the other one is fluorine is always going to be a -1. Okay, fluorine is a most electronegative element. So fluorine, if it's in a compound, it's a -1. So if we have OF2, the fluorine is still going to be the -1. The oxygen will actually be a +2, but that's kind of off. It's out there. Okay, some of you might have caught that joke. It's off the board now. Okay, fun stuff, right? Okay, the next rule that we're going to look at are the halogens are going to be generally -1 unless they're combined with a more electronegative element, oxygen, or a halogen that is higher on the periodic table. Okay. And in case you're wondering, do I have a periodic table in here? I do. It's up on the wall over here. It's not the greatest periodic table because I couldn't figure out how to put it in the video and still show the whiteboard like I want to, but it's there. Okay, but if it's higher on the, like fluorine is higher than chlorine. If fluorine and chlorine are bonded together, fluorine will get the -1 charge. If chlorine and bromine are bonded together, chlorine is higher than bromine, chlorine will get the -1 charge. Okay, let's see. The oxidation number of hydrogen is a +1 in most compounds. Now realize that you can also have hydrogen which has 1 electron and 1 proton. Hydrogen can also become a hydride. So if you've combined it with a metal like lithium hydride, the hydrogen is actually negative in that particular case. Most of the time we're going to see hydrogen as a +1, but be aware that hydrides exist and they're fairly important. There are some batteries that take advantage of the hydride, and you may end up seeing some of those, especially in your lifetime, if it turns out the hydrides turn to be an important aspect of batteries of the future. I don't know whether that's going to happen or not. I've done a decent amount of study with batteries, but I haven't really worked at all with the hydrides. But I don't rule them out. Just because I haven't studied them personally doesn't mean somebody else may come out with a breakthrough. All right. The other elements, how do we find out? Okay, well, what we're going to do is just simple algebra. If I have a compound, the sum of the elements in the compound are going to be 0. If I have an ion, the sum of the elements in the ion's oxidation number is going to be equal to the charge on the ion. So let's go ahead and apply these rules to this particular problem here that we see. Now I see aluminum. Aluminum, it's an element all by itself. First rule applies. Its oxidation number is 0. I have the next one is manganese and oxygen. I'll come back to that one here in a second. Let's go over here to the easy ones. Here I have an element that is a monatomic ion. Our second rule, the charge on a monatomic ion is the same as the oxidation number. So this is going to be a +3. This is going to be a +2. Now, what about this permanganate? Now, I already showed you how water works out. Now, oxygen is always going to be a -2, unless it's in one of those weird ones. This isn't one of those. So we put a -2. And if I look, whatever the manganese, its oxidation number is, now let's go with a number of them. I have 4 -2s, and that's going to be equal to a total of this charge here, which is a -1. What is manganese oxidate? What is manganese's oxidation number in this case? It's going to be, right? Okay, so we're good so far. All we have done, however, is look at the problem and assign oxidation numbers. Now, again, I went back through and reviewed how to assign oxidation numbers. So 20 minutes into the class, we've looked at a problem, we've written some numbers above it, okay? But I also reviewed oxidation and reduction. And if I look here, I'm going to have 2 elements changing their charge. Now, one of the most important rules is you cannot have an oxidation without a reduction. You can't have something gain electrons if something else didn't contribute them. Okay? Now, that reduction may occur remotely or it may occur right there. In this case, we're going to look at the oxidation and reduction. So we're going to write the 2 things that have a change in oxidation numbers. Now, I'm going to underline the 2 elements. This one is relatively easy. I know aluminum goes from a 0 to a +3, okay? And I see that the manganese here goes from a +7 to a +2. So those are my 2 things that change oxidation numbers. So when I write this out, what I want to do is write what is called a half reaction. I'm just going to take a look at the aluminum. I'm going to write the aluminum solid over here, and I'm going to write the aluminum 3+ over here. Now, if I pay attention to electrons, electrons are negatively charged. In order to go from a neutral aluminum to a 3+ charge, it has to lose electrons. And I'm going to write that. It just so happens in this particular case that it loses 3 electrons. Al 3+ 3 electrons. Losing electrons. Of the electrons are on the right. Okay. Leo, this is our oxidation half reaction. So for something that's going to be really important for us to be able to identify which is oxidation and which is reduction. For right now, we just need to know we have to have electrons on the right side on one and electrons on the other side on the other. The other reaction that we have is manganese, MnO4-. The manganese goes from a +7 to a +2. Now I'm going to write this out, and I'm just going to worry about the manganese. I know there's an oxygen in there. We'll take care of the oxygen later. There are people who teach this that say, you need to take care of that oxygen right now. That's perfectly fine if you learn how to do it. I'm teaching a little bit different method, which I think is a bit simpler. So we're just going to look. Now, in this reaction, I have 1 manganese on the left and 1 manganese on the right. I have 1 aluminum on the left, 1 aluminum on the right. if the element that changes oxidation number has either a coefficient, which is going to be unlikely because we're adding those to balance the equation, or if it were to have a subscript here, for example, if oxygen was the one that changed, I would have to balance the element undergoing a change in oxidation, okay? Now, manganese goes from a +7 to a +2. How does it go from a +7 to a +2? Well, I have to add electrons. And if I want to figure it out, how many electrons do I need? +7, +2. It's going to be 5. So I've done a relatively simple thing. I have written my oxidation numbers, and now I have written my two half reactions here. Now, for what's important later, this is our oxidation. This is our reduction. And a common abbreviation for these types of reactions, instead of saying an oxidation reduction reaction, we say redox, okay? And no, that's no relation to Babe the Blue Ox from Albany, okay? All right, we've done all this and we don't have a balanced equation yet, right? Well, why not? Now remember I said for every oxidation there has to be a reduction. If electrons are gained, they have to be lost somewhere else. Well, not only do we have to have electrons lost and gained, we have to have the same number of electrons gained and lost. So we're going to take a look at this one, and we're going to say, okay, so if 5 electrons are lost here and 3 are gained here, I need to balance that. So what I'm going to do is I'm going to balance the electrons in my two half reactions. What I do is I look for the least common multiple. And I know you're thinking, least common multiple. That was one of those things that we had to do in like middle school math. And we're like, we're never going to use this in our lives. And now that you have never used it in your life since then, you don't remember what that is. Well, 3 and 5 are both prime numbers. So that makes it kind of easy. The least common multiple of 3 and 5 is going to be 15. How do I get 15 electrons out of 3? Well, what I'm going to do is I am going to multiply this half reaction by 5 and this half reaction by 3. Okay, so in doing this, I have taken into account that this one loses 5 electrons. I have 3 of these half reactions occurring. This one loses 3 electrons. I think I said that wrong. This one gains 5 electrons. It has to gain 15. This one loses 15. So I have 5 of this reaction, 3 of this reaction. Relatively simple steps. This is easy after you start doing it a little bit, okay? Now, in this case, there's a couple other things that I want to point out. When you have this 3 here, this 3 goes for everything within the parentheses. This 5 goes with everything within the parentheses. So what I'm going to do is I'm going to take these coefficients and I'm going to carry them up into my overall reaction, okay? So aluminum, I'm going to have 5 aluminums here and I'm going to have 5 aluminums there. The manganeses, I'm going to have 3 permanganate. I need to move my plus sign a little bit there. 3 permanganates and 3 manganeses. And I know you're thinking, okay, so I got coefficients up there, but still, oxygen's here. No oxygen's over here, right? Okay, well, we're going to add something to it. And the key is this whole thing that we have an acidic solution. In an acidic solution, we have 2 things that are present. First of all, our solvent H2O is very much present. We've got waters all over the place. We got more waters than we got everything else by a factor of millions, okay? I also have hydroniums, okay? And to simplify this, there are people who say, well, you take and you start balancing things and balancing things. There is a simpler way to do this. I want to look at the overall charge balance of this reaction. And what do I mean by charge balance? This has a charge of 0. This has an oxidation number of a -1. This has actually a charge of a -1. This has a charge of a +3. This has a charge of a +2. So in addition to looking at the oxidation numbers, I'm going to look at the charges. Now notice that I wrote the oxidation number in red and the charges in black. I do that to help you see that a little bit easier. I had tried to use purple, but I don't know if you can see the purple. When I look at the screen over here, all I see is red and black, and whatever this color is here, which might be blue. So hopefully you can see the colors a little better. If I add all the things that have a charge over here, and I'm going to use red because I can see the red, hopefully you can, even though I wrote oxidation numbers in red and charges in black. Over here, this has a charge of 0, so it doesn't matter how many of them I have. This has 0 contribution to the charge. I have 3 permanganates. Each permanganate is a -1. So over here, my entire charge is going to be a -3. Pretty simple. Now here, wow, this is going to be some big numbers because I have 5 3+ aluminums, that's 15, and I have 3 2+ manganese, that's 6. This gives me a +21. In order to balance that, I need to add one of these two. Now, only one of these has a charge to it. I don't care how many waters I add to either side, I am not going to have any effect on the overall charge of this equation by adding water. We'll come back to waters later. Now, in order to add waters, I need to figure out, okay, which side of the equation do I need to add waters to? Now I'm going to leave the great white spot here because I need the space here. But in order to add waters, I know that I have more positives over here and negatives over here. So I need to add the positive ions to the left side. So I'm going to take and add waters. Okay, now how many waters am I going to add? I have a difference of 24. And why am I saying waters? It must be Monday. Water doesn't have a charge. Well, okay. So if you pay the water bill, maybe water does have a charge that way. But that's not what we're talking about. I have to add H3O pluses here. Now, in order to add H3O pluses, I need to know the number of them. I have, in order to get a +21 on this side, I need to add 24 of them. That's a lot. That's a big number, but we may end up with some big numbers in here. Okay. I now have an overall charge balance. But if I have 24 waters, I have 72 hydrogens? I may have made a mistake here. I'll have to go back through and see. Okay, but anyway, so when I do this, I look and I see that, okay, so 24, in order to have that many hydrogens on the right side, I'm going to balance, and I have to write my waters on this side. Now, in this case, I have 72 hydrogens on the left, 72 hydrogens on the right. On the right side, I have 36 oxygens, and here I have 24, 3 times 4 is 12, 36 oxygens on the left side. Holy cow, the whole thing balanced. That looked pretty simple, right? You know, half hour into it, and we have balanced this one particular reaction. So it's going to take a little bit of practice for you to do this, okay? I'm going to go ahead and go through one more example, and then I'm going to leave you a little bit of practice here. Now, do you want me to do a more complicated, or do you want me to do a basic one? Should be 18. No, it shouldn't be 18. It's 24, okay? Because I need to have an overall charge of +21 over here. And notice that the 24 did work out. All right. I should do a basic one, right? All right. Now, normally when I say a basic one, that means a simple one. But in chemistry, we know basic means that it's not acidic, it's basic. So we're going to do a basic example. You have this. Theoretically, this is recording and I will get it posted so you can go back through and watch this. So I'm just going to erase it now. And I'm going to write another problem on the board. And this one's going to be basic. Okay. I have to get one of those whiteboard cleaner things here and get that cleaned up here before too many more lectures. All right. So I have a problem that I looked at ahead of time that's basic. And it's not the most difficult. So I have magnesium, which is a solid, plus OCl minus. We usually talk about this with the that, and you think, oh, do we ever see that? Well, this is hypochlorite, the ion commonly found in bleach. So this is not something that's just out of left field. This is what we see in bleach. So magnesium reacts with bleach to get magnesium hydroxide plus chlorine. And the magnesium hydroxide actually precipitates out. Okay. Now this one is going to be a little bit, well, maybe I shouldn't do this one. All right, I am going to leave this one for you to do, and this is a basic one. I put it up there. I'm going to let you do this one for a practice. Okay, now that I've got that. And then I am going to pull one more problem out here. That is a basic one that's going to be a little bit more fun for us to do. This one both of these are 0, and both of these have the charge. So when I get the electrons balanced, it'll balance fairly simply. So this is a fun one that I have for you to do, but I had planned on having more time. So pause your video if you're doing it, or do this later. There's a fun one for you to try. We are going to look at a different one here. And this one occurs in basic solution. And we'll stick with the permanganate. And I keep squinting here because it's hard for me to see the way I've set up the lighting in here when I look down. Oh, that one's going to be too hard here. I realize that one. Let me show you that one too, because there's something that I want to point out with this. Okay, let's see. Yeah, in this one, notice that I have some manganese sulfide plus sulfur. So I'm going to have some sulfurs that both undergo a change in oxidation number and some that do not undergo a change in oxidation number. And I will go ahead and show you this on a video that I'll just post separately. So I will go ahead and work that one later, but I'll post that video on Canvas. This is kind of a fun one, but not what I want to get into. All right, so I had marked both of these to show you some things, and I want you to go ahead and try those. But again, I thought I was going to have more time, and it's 10:35. So now let's go to the fun one that I want to finish out with. Okay, so we've got cyanide. Are you seeing what I have up here? Okay, and that reacts with permanganate. Now, the fun thing about cyanide is anytime we have cyanide in a reaction, we want to keep it basic. The reason we want to keep it basic is because if I put hydrogen here, if I make it acidic, I'm going to release hydrogen cyanide gas that is poisonous and deadly, and we don't want to do that. So we want to keep this one basic. So not only will this be basic, it will be very basic. And this is going to form the cyanide ion. And the other thing that it is going to form is manganese dioxide. And I don't know if I have left enough room, so I'm going to move this here. And that happens to be a solvent. All right. Doing this, what is our first step? We are going to assign oxidation numbers. Okay. And let me stick the thing back up here, at least for the moment. Okay, I guess that C is not showing up really well here. Let me make that a little bit more clear here. Okay, I made it clear, but then it wasn't a very good C. There. So I guess some of you could have said, oh, hey, when you first put it out there, we weren't seeing it, okay? All right. Taking a look at this, oxidation numbers. Do I have any monatomic ions? No. So I need to start with this. Now, this one I chose because I need to review something. If I go through the oxidation number rules, it doesn't tell me anything how to do this one. So what we're going to do is we find the more electronegative of these two is going to receive a charge as if it were an anion. So nitrogen is normally an anion with a -3 charge. So it's going to be a -3. In order for carbon and nitrogen to add up to this, whatever carbon's is plus a -3 has to be equal to a -1. So carbon is going to be a +2. Okay. The permanganate we did last time, so you can review that if you want. That's going to be a +1 and a -2. I'm going to skip over here to the permanganate because the manganese dioxide. In this case, oxygen is always going to be a -2, and there's 2 -2s. So that permanganate is going to go to manganese dioxide at a +4. This one is the tricky one here. Okay, oxygen is always going to be a -2. Nitrogen is still going to be a -3. It's still more electronegative than carbon. So I'm going to have whatever carbon's is here plus a -3 plus a -2, which is equal to 0. Okay. Carbon in this case is going to be a +4. Okay. All right. Little sip of coffee here. Half reactions. The two elements that undergo a change. Nitrogen doesn't change, but carbon does. Oxygen doesn't, but manganese does. Now notice I got oxygens all over the place here, which is okay because I'm going to balance those by something else other than just looking at oxygens. So let's look at our first half reaction. The first element that I come across that changes is carbon. And it goes from a +2 to a +4. How can it do that? It has to lose 2 electrons. Okay. And sometimes, especially as you first start, it might help to figure out, okay, if I want to balance this out, where do I have to put the negative electrons? Here on the right. Wouldn't that carbon be a 5? No. It adds to a -1. Okay. Because 3 and 2 are -5. The negative comes from the charge of the permanganate. Okay. All right. So let's see here. Permanganate goes to. I have 1 manganese here, 1 manganese here. I have to go from a +7 to a +4. So I need to add 3 electrons here. Okay, simple. Okay, are my electrons balanced? No. Sometimes it happens where you do this and you come up with the electrons that are balanced. Okay. The other thing, most common mistake people make on this is, for example, if I had I minus here and I2 over here, I would need to have 2 I minuses. People forget that a lot. That's the easiest mistake to make. I know, because I make that mistake all the time when I do that. All right, balancing electrons, 2 and 3, least common multiple of that is 6. So in order to do this, I am going to multiply this entire reaction by 3, this entire reaction by 2, okay? Carrying my coefficients up here, 3, and again, I'm gonna have to pull that off, 3Cn minus, and 3CNO minus, 2 MnO4s, and 2 MnO2s. Now, this is a basic solution. I probably should have written that somewhere up here. I'm going to do that now. Although I did talk about it being basic a number of times, we need to do that. Now, for a basic solution, I don't have hydroniums in abundance. I have hydroxides and H2Os. Which one of these two has a charge? The hydroxide. Oh! I'll let that sink in for a minute. All right. So let's look at the charges here. I have 3 negatives and 2 negatives. This gives me a total of a -5 over here. Here I have 3 negatives and 2 neutrals. This gives me a -3 over here. So in order to do this, I need to add 2 negative charges to the right side of the equation. So I'm going to put plus 2OH minus. And then you look at that and you go, uh-oh. Gotta throw those jokes in here. Now, in the entire reaction, I don't have any hydrogens anywhere. So the only way I can come up with hydrogens is H2O. Now let's go ahead and double check and make sure that I haven't made a mistake by checking the oxygens. Notice I don't go and check anything else at this point unless I had one, like the one where I had the sulfur in 2 different places. But here, if I look at the oxygens, I have 1 oxygen here and 2 times 4 is 8 oxygens here. This gives me a total of 9 oxygens here. I have 3 oxygens here. I have 2 times 2 is 4 oxygens here, and I have 2 oxygens there. This gives me 9 oxygens on this side. So overall, this gives me a nice balanced equation. Okay. All right. So I have gone through how to balance oxidation reduction problems, but I think you need to get a little practice at this. So I don't want you to wait until the very end to do everything here. So between now and Wednesday, I want you to go ahead and practice balancing equations and just look in your book at problems 3 through 6 in chapter 19. Take a look at those between now and Wednesday. I think I will have you submit some of those at some point before the rest of them are due. It will still be part of the chapter 19 assignment. But as this is Holy Week, I'm not going to make it due this week. But do yourself a favor. Try balancing equations. Try doing the balancing redox this week. If you do nothing else this week, that's going to be the most important thing. So again, and I will make an announcement on Canvas. So we've got this. So look at problems 3 to 6 in chapter 19 between now and Wednesday. How did I know to only add one H2O? I had two hydroxides over here, two hydrogens. Two hydrogens, one water. Okay. Oh, good. Answered, Min. All right. The other thing I want to talk about a little bit is the lab that will be up this week. For the lab, I will have you going to a simulation site and doing measurements with that. I will also post, you can read through the lab in the lab manual. I can't quite have you do everything that's in there on the simulation site. So I'm going to alter the procedure, and that will be posted. The way it's going, that will be posted tomorrow morning, along with a video. Now I say tomorrow morning, I would like to say I will have it up bright and early at 8 o'clock, but I will do everything. I will have at least the procedure up by 8 o'clock. The video may not be up until closer to 9. The other thing that I need to mention, the chapter 18 assignment, the due date for that is still today, and there's, I think, 4 problems that I'm asking you to turn in. Please picture, scan, however you need to, and send those in. I will get those taken care of, but that is due by the end of the day today. And let's see, what time do we have here? I need to put a clock up here. Oh, 10:44. Okay, we had a little bit more time than I thought we did. With that, the chapter 19, you are gonna, I would expect to have some written problems on chapter 19 as the quiz, not this coming Friday, because this coming Friday is Good Friday, but the following Friday. I will probably have 3 written problems for you to do. One will be a balancing oxidation reduction problem. And I think on that one, I'm not going to have you stop and do that. I will give you 50 minutes for that particular quiz. And I'll post information about that as well. All right, with that, I'm going to go ahead and let's see. For the lab, what do we do with delta H and delta S values for gaseous calcium and hydroxide? Well, at some point, you need to find the literature value for delta H and delta S for that particular reaction, right? How are you going to find that? These 2 are not in the book, so I found several places there. What oxidation are you trying to make it equal 0? Okay. With oxidation, what you want is the oxidation number. Let me put this up here. I can't write here. What number is up here? There isn't one. So 0. Okay. So that's going to be 0. For permanganate, I want the sum of the oxidation numbers to be equal to that charge, which is negative. And for chapter 19 homework due, when is that due? I will give you a due date for that. Right now, act like problems 3, 4, 5, and 6 are due at the end of this week, because I want you to do that before we go on to the next thing. The chapter 19 homework will be the same as the syllabus. I will, again, at some point, post which problems I'm going to collect and grade, but I still expect you to do them all. And when you come up with problems, I expect you to ask about those. I have already decided which ones I'm grading, so if you happen to ask about one that I'm going to grade, I will still answer that. But once I post which ones I'm going to grade, I'll stop answering questions about those particular 3 or 4 problems. And as far as the chapter 19 homework due, the written quiz is probably going to be not this Friday, but next Friday. So I will have some chapter 19 problems that will be due the following Monday, and then we will cover chapter 25. Now, again, I say that, we'll see how long it takes me to get through all of chapter 19. Remember, I'm going to post 2 PowerPoints. One is just a review of what we've done today with a little bit slower, and the other one is going to be the remainder of chapter 19. I'll probably have that one up on Wednesday. All right. Any other questions to post here? We still have like a couple minutes, but all right. So let's see. All right. Well, with no other questions at this moment, again, if you have questions over the lab that is due, I think I put it as due at the end of the day. If I didn't put it due at the end of the day, it's due at the end of the day. The thermodynamics lab is due at midnight tonight. The chapter 18 problems, those 4 that I posted, are going to be due there at midnight tonight. For turning in the take-home exam, do we post photos of our written work or submit it in a document? Yes. For the take-home exam, it's okay for you to do it either way. If you want to type everything out into it, that's fine. If you want to do a mixture of typing into the document, by the way, the take-home exam is on Canvas. If you want to open it up and just type in stuff there, that's fine. So those are 2 possibilities for it. If you would prefer to just write everything in there and take pictures of it and submit it, that's fine. I will be putting a submission for that on Canvas, and you can submit multiple pages if you want. It will act like it's submitting multiple assignments. All right. I think that is the last question. With that, Monday of Holy Week, where are the recordings of these lectures? For the ones that I remember to record, I will put them on Canvas. So far, I'm 1 for 3. And I think that one is on Canvas, or if it's not, it will be. Today's, I do have a recording of it. This will be put on Canvas. Actually, I'll put it on YouTube, and there'll be a link to it. You can probably find my channel, even though it's not well advertised. Maybe I'll send a link out for it. But I'm posting all these on my YouTube channel that I have through Newman, and that's where you're going to find it. How do I want you to submit the bibliography? I will have a separate file for that. On the bibliography, if it's not your textbook that you have here, I really do want you to submit a bibliography that contains the URL, even if that's not the format you're used to, and you'll submit that separately. There will be a separate place, so there'll be the take-home exam and the bibliography. The bibliography will say 0 points on it, but I still am going to use that to do that. All right? Okay. I don't want just the URL. I want an actual full reference, either MLA, APA, ACS, whatever you want. But if you're doing MLA, I don't remember whether MLA requires you to put the URL in there. I want you to add it in there. Thank you.